This question is from May, June 19, paper 11. A cylindrical iceberg of height h floats in seawater. The top of the iceberg is at height h above the surface of the water. The density of the ice is rho I and the density of the seawater is rho W. What is the height, lowercase h, of the iceberg above the seawater? Since the iceberg floats, then the iceberg weight is equal to the upthrust force. The upthrust force is equal to the weight of the mass of the water displaced by the iceberg, which is the bottom part that is submerged. The weight of the iceberg is mass of the iceberg times g, and the upthrust force is the weight corresponded to the mass of the water displaced times g. We are going to cancel those two g's. Then what is left is the mass of the iceberg is equal to the mass of the water displaced. But gets better. We can use the density formula and rearrange this formula in terms of the mass, which is density times the volume. Now let's do our substitution for each terms of this equation. So on this side, mass of the iceberg. So the formula now is the density of the iceberg times the volume of the iceberg. And the mass of the water displaced in terms of this new formula is the density of the seawater times the volume displaced by the iceberg. The volume of the ice is the cross-sectional area of the cylinder times the height, which is the uppercase H. The volume of water displaced corresponds to the bottom part of the cylindrical iceberg, which is the cross-sectional area of the iceberg, A, times the difference of this height, because it's just the bottom part. So uppercase H minus lowercase h. Now in this slide, I have a sequence of substitutions. Just follow along. So here the volume of the ice is given A times uppercase H, and the volume of the water displaced is the cross-sectional area of the iceberg times the difference in height, which I explained before. Now, we can cancel both A's. And what is left is the density of the ice times H is equal to the density of the water times the difference in height. Doing distribution is we have the density of the seawater times H minus the density of the seawater times lowercase h. Because I want to calculate the value of lowercase h, which is the section of the iceberg that is outside the water, I'm going to rearrange here. So this guy stay where it is, but I move it to the left side of the equation. And the density of the ice times h minus the density of the seawater times uppercase h. Just to make a little bit better, I'm going to switch the sign of the whole expression. Now the density of the seawater is positive, this one is negative, and this one is negative. Now I'm going to divide the whole term by the density of the seawater. And notice that the density of the ice times h is also negative. I didn't change anything. Okay, now I'm going to divide, and my final expression is 1 minus the density of the ice divided by the density of the water, and H multiplies the whole thing. So the answer that matches with the result of my calculation is option A.